So now that we've done all the drawings for the polar curves, what do you do now that you know how to draw these things? What can you use them for? Well, there's a couple of things we can do. Obviously, calculus lets us find area between two curves. It lets us find the area between a curve and an axis. It lets us find slopes of curves. So all those types of things that we applied to curves in rectangular form apply to curves in polar form, although they look just a little bit different. So suppose you started with a sector, right? So you've got your initial ray, and you've got some radius and a delta theta. So I'm going to take a little piece of this curve, right? There's a polar curve out here somewhere. I'm going to call this little piece delta theta, and I'm going to call that the radius. So really that should be like that. Okay, little piece. If I want to find the area of a sector of a circle, what do? The area of one sector is going to be a slice. So if you think of taking a slice of pizza, except an infinitesimally small slice of pizza, it's going to be how much of the circle you have out of 2 pi, right? That's the fraction of the circle you have, and you want to multiply that by the area of a whole circle, which is pi r squared. So the pi's cancel out, right? We can get rid of the pi's top and bottom. So the area of one sector then, if we rearrange terms just a little bit, becomes delta theta times 1/2 times r squared, or if we simplify it a little bit, 1/2 r squared delta theta. So that's the area of one sector. If we want to take the sum of all those sectors, and we could take a Riemann sum of all those sectors, and that will give us the area that's inside the polar curve. So can you see where this is heading? If you have a Riemann sum, that should lead us to the idea of an integral. So the area inside a polar curve, right? That's where we're looking for the formula. Area inside a polar curve. Okay, take what I have up there and translate it as an integral. So 1/2 can go on the outside. My limits of integration would be a and b. Those are both angle measures. And it's going to be an r squared, and the delta theta becomes my d theta. So the area inside a polar curve, 1/2 r squared d theta, integrated from endpoint to endpoint. So the formula isn't hard. Sometimes the mechanics got a little bit messy because you're doing integration with trig functions, but aside from that, not bad at all. So let's take a look at an example. Suppose I want to find the area inside of that polar curve we did the other day, which was r equals 7 minus 7 sine theta. Now remember what this one was. This was the cardioid. It sat this way, and the other half went like this. If you wanted to change the cardioid, you could change the sines and cosines, but this one happened to be a cardioid that looked like this. Now, limits of integration wise, I'm going to go from 0 to 2 pi. You could find half the heart and then double it, but just be careful what you use for your limits of integration. If you say I'm going to go from 0 to 2 pi and double it, that's not 0 to pi and double it. That's not going to work because that's 0 and that's pi. You're going to end up finding this area on the top half, and then when you double it, you're not going to get the area of the whole thing. So you could find this area over here, but remember that means then you're integrating from negative pi over 2 to positive pi over 2. And then doubling it. So you can use symmetry, just make sure you're using it correctly. All right, I'm going to just go from 0 to 2 pi because I think it's easier. So I'm going to do 1/2 the integral from 0 to 2 pi of r squared d theta. Well, this thing is r. So r is 7 minus 7 sine theta. That's my r squared d theta. All right. Like I said, the rest of this is mechanics, so expand out that binomial. Remember that you actually get 3 pieces. You get a 49, you get a 98 sine theta, and you get a 49 sine squared theta. Okay? That's what happens when you expand out that squared term. And now, I don't know, why not pull the 49 on the outside? Pull the 49 on the outside, and I get 49 halves, right? Because there's still that 1/2 there. Don't forget we haven't integrated yet, so I still have a 0 to 2 pi of 1 minus 2 sine theta plus sine squared theta. Now, what am I going to do with that sine squared theta? I need a little substitution. So take that sine squared theta and replace it with 1 minus cosine 2 theta over 2. Right, that's one of our identities that can help us to get rid of a squared term. So 1 minus cosine 2 theta over 2 will get rid of that sine squared. All right, carry this down to the next line, and I get 49 halves, integral from 0 to 2 pi of 1 minus 2 sine theta plus a half, right? The half comes from this, minus a half cosine 2 theta. And then combine like terms. So you got a 1 over here, and you got a half over there. Combine the two of them together. Try to simplify this as much as you can before you integrate it. Otherwise, you'll end up doing double the work at the end. So 1 plus a half gives me 3 halves minus 2 sine theta minus a 1 half cosine of 2 theta. And now at this step, we're ready to actually integrate. Remember, we haven't integrated anything so far. Now we're actually going to integrate. So let's leave the 49 halves on the outside. When you integrate with respect to theta, that 3 halves becomes a 3 halves theta. Minus, now if you integrate sine, you'll get negative cosine. So negative negative makes a positive. So plus 2 cosine theta. When you integrate cosine, you get sine. So you get minus sine of 2 theta. But now divided by 2, right? That's a chain rule from the cosine of 2 theta. And then the other 2 is already there, so I end up with a 4. Okay. We're going to evaluate this at 2 pi and at 0. So this gives me 49 halves. I put a 2 pi in for theta, and I get 3 halves times 2 pi. I put a 2 pi in for cosine, and so the cosine of 2 pi is just 1. 2 times 1 is 2. Sine of 2 pi is 0. Now from that, I have to subtract everything evaluated at 0, which is what? 3 halves times 0 is 0. 2 times the cosine of 0 is 2. And really, that's it. And you realize that that and that goes away. That and that goes away. And the whole problem just collapses. I get 49 halves times 3 pi. So that is 147 pi over 2. And that is the area inside of that polar curve. All right, let's try another one. Let's try one that involves a rose. So this time we'll look at the area inside R equals 4 cosine of 2 theta. Now from graphing it, you know that in order to get this entire rose, you're going to have to go from 0 to 2 pi. So let's try it that way, and then we'll look at one other way to do it. Remember the formula for the area inside a polar curve, integral from a to b, in this case 0 to 2 pi, 1 half r squared, so 4 cosine of 2 theta squared d theta. All right, when I square this, don't forget I square the 4 and I get 16. All right, so square the 4 and you get a 16. Square the cosine, well, you get a cosine squared. Don't square the 2 in front of the theta, just the cosine squared. So let's take the 16 here and the 1 half here and make it an 8. So I'll get the area is equal to 8, integral from 0 to 2 pi of cosine squared 2 theta. Now, what do I do with a cosine squared 2 theta? If I know that cosine squared theta is 1 plus cosine 2 theta over 2. What if I replace that theta with a 2 theta? Then I'm going to get a formula that says the cosine squared of 2 theta is 1 plus cosine 4 theta over 2. And that's what goes in this integral. I'm going to end up with 1 plus cosine 4 theta over 2. Now, why not take the 8 that's on the outside and the 2 that's on the inside and simplify it once more? Make it that the area is equal to 4 times the integral from 0 to 2 pi of 1 plus the cosine of 4 theta. And that becomes a much easier thing to integrate. All right, if I carry that across, I end up with 4 times theta plus, now if I integrate cosine, I'm going to get sine. So sine 4 theta over 4, evaluated at 2 pi and at 0. And this comes to an end pretty quick because putting a 2 pi in for theta up here gives you the sine of 8 pi, which is 0. The sine of 0 is 0. So this whole thing simply becomes 4 times 2 pi, which is 8 pi. Now, what was my other option? When I had set up this rose, the first thing the rose did was it came from here down there. How far did it go? Well, if this is a cosine of 2 theta, that must mean that there's 4 petals on this rose. So if I went from 0 to pi over 4 and found the area of just this one piece, then there would be 8 of them altogether, right? There would be another little piece here, another piece here, another piece here, and then 4 more when you trace the flower on that side and that side. So I could, right, here's another option. I could have integrated 1/2 the integral from 0 to pi over 4 of 4 cosine 2 theta squared, and then multiply it by 8. So I'm going to sort of steal the answer that I have up here, the 4 times theta plus sine 4 theta over 4. So I'll take that thing that's in blue over there, the 4 times theta plus sine of 4 theta over 4, except this time, instead of going from 0 to 2 pi, I'm going to set my limits of integration at 0 to pi over 4, and I'm going to take that answer, I'm going to multiply it by 8, because there's 8 of those little half leaves, I guess, for lack of a better thing to call them. So this gives me 32. The theta is pi over 4. What happens when I put the pi over 4 in for the sine of 4 theta, I get the sine of 4 times pi over 4, and that's just the sine of pi, which is 0, divided by 4 is still 0. When you throw the zeros, everything zeroes out, and you end up with 8 pi that way also. So it doesn't matter whether you went from 0 to pi over 4 and multiplied it by 8, or if you just went from 0 to pi over 2, I actually think that's a little bit easier in this case, because, I don't know, does it all in one step. I don't have to worry about multiplying by 8 at the end. All right, let's take a look at one more, and then we'll look at area in between curves. All right, suppose I want to find the area inside a lemniscate. So let's find the area inside that lemniscate that we graphed the other day, which is r squared equals 5 cosine squared, or 5 cosine of 2 theta. Remember we said that was a lemniscate. And I want to find the area inside. Now remember what the area formula looks like. The area formula is the integral 1/2 r squared d theta. Well, the first thing you notice is that this thing is r squared, and that thing is also r squared. So don't square this when you put it in, because it's already squared. The other thing is, remember something that was different about the lemniscate is that it had places where it didn't exist. So it came down like this, and then between like pi over 4, in this particular case, not in every case, but in this case, remember between pi over 4 and 3 pi over 4, it didn't exist because it was below the axis. So I've got to be careful about picking my limits of integration for this. I can't pick from like 0 to 2 pi because there's parts where the graph doesn't exist. So I'm going to pick the part between 0 and pi over 4. And then I'm going to multiply that answer by 4 because I get a little piece here, I get a little piece here, I get a little piece there, and a little piece there. So I've already got the 1/2 that came from the formula. I'm going to multiply that by 4. My r squared is 5 cosine of 2 theta. No need to square anything, d theta. So this looks like not a terrible problem. Pull that constant on the outside. Half of 4 is 2. I'm going to pull the 5 out. 0 to pi over 4. Cosine 2 theta d theta. If I take the antiderivative of cosine, I get sine. So I get 10 times the sine of 2 theta over 2. All right, chain rule. Pi over 4 and 0. Well, the sine of 0 is 0. That makes the bottom limit of integration easy. Up on the top, I get 5 times the sine of 2 times pi over 4. 2 pi over 4 is pi over 2. The sine of pi over 2 is 1. That makes the area inside of that lemniscate an integer. How cool is that? After all that work, the area inside the curve is an integer. All right, let's take a look at one other case that involves area, and that is area between two curves. In rectangular coordinates, you know how to find the area between two curves. If I had given you a function that looked like this, let's say a parabola and a line, you would draw those little rectangles to find the area between the two curves. You would take top function minus bottom function and find the area that way. Or if you were integrating with respect to y, you would do right curve minus left curve and draw those little rectangles and find the area that way. Well, what if you want to find the area between two polar curves? What might that look like? Well, suppose I have one polar curve out here and another polar curve here. And I'm going to look at taking a little slice like we did before, right? Certain radius, except now I'm going to have two different radii. One radius will go from the pole all the way to the points on the outside. I'm going to call that capital R for the big radius. The little radius goes from the center to a point on the first curve, so that's the little radius. If this is still my delta theta in the middle, right, that's the angle, this is the area that I'm trying to find, this area in here. Well, this should bring back memories of washers, right? Big R's minus little r squares. If I take the whole thing, pi times big R squared times the angle that's in there, and then subtract off the little piece. So what's the little piece? The little piece is a pi r squared delta theta. Now let's just be specific here. We're talking about a fraction of the whole area. So we're talking about this over 2 pi and that over 2 pi. And if you look at the way this is structured, there's a lot that's in common between these two things. So first of all, let's knock the pi's out. And I end up with a delta theta over 2 times big R squared minus a delta theta over 2 times little r squared. All right, this is starting to look like a formula. Let's pull the 1/2 on the outside. I'm left with a big R squared minus little r squared, and then I'm going to put my delta theta over here. So this is one slice, right? Or in terms of angle measures, we think of it as one slice, like a sector of a circle slice of pizza. What if I now made a general formula? So in general, if I'm looking for a formula, area between two polar curves, okay, can you see how taking a Riemann sum of this might lead up to a formula for area? We still have our 1/2. We have limits of integration. Big R squared minus little r squared d theta. Now notice that the big R and the little r are both functions of theta. So there will come times when we say we're going to set up this problem but not actually solve it and get a value, because we're back to some of those issues we had at the beginning of the course when we were dealing with disks and washers and other very complicated functions, and sometimes it just wasn't worth sitting there and knocking through each of the problems, or the formulas went beyond what we kind of knew, although we know a lot more now than we did at the beginning. So let's take a look at one specific problem. I'm going to try not to get too complicated on these, but let's find the area inside this function, r equals 3 plus 3 cosine theta, and outside 3 plus 3 sine theta. Right, so inside one, outside the other. I guess I could be more specific in terms of quadrants and limits and all that, but let's see if we can figure out without that information. The first thing is we need a graph, so you are going to have some idea what these things look like. These things both look like circles, right? If I remove those 3's, I get r equals 3 cosine theta, r equals 3 sine theta. Those are both circles. How do they behave? Well, they're not technically circles. They're really cardioids, but still, they behave in similar ways. So let's see. Cosine of 0 is going to be 1. So 3 times 1 is 3, plus 3 is 6. So here, let's color code these. That guy over here will be the red one. He starts here at 6, and then what does he do? He works his way back towards the pole, overlaps it a little bit, so it's a sideways cardioid that comes like this, and out like that. So that's what the 1 looks like. What does the other one look like? Well, the sine of 0 is 0. Add 3 to it and you get 3. So this one's going to start here at 3. What if I put a pi over 2 in for the sine? Sine of pi over 2 is 1. 1 times 3 is 3. Plus 3 is 6. Now this guy comes up like this. Right, terrible drawing for a cardioid on a tablet, but we'll see what we can do. Okay. Now, if I look at this little piece in the middle, I wanted it inside the red one and outside the blue one. Well, where is outside the blue one? It can't be anything past this point here, right? Outside the blue one, but inside the red one? Well, let me specify that I want it in quadrant 1. In quadrant 1, then, the only place that's inside the red one and outside the blue one is that piece over there. Draw yourself a sector that goes from the center to a point on the outside like this, right? Now can you see that the red one is the big R, because that's the one that's furthest away? So that's going to be your 3 plus 3 cosine theta. And then your little r is the blue one. The little r is your 3 plus 3 sine theta. Because you're looking for the one that's farthest away and the one that's closest. The red one is the one that's farthest away from the pole. The blue one is the one that's closest. All right. Next thing then I got to consider is limits of integration. I'm going to start at 0, but where do I end? Well, I end where the two functions intersect each other. So where does 3 plus 3 cosine theta equal 3 plus 3 sine theta? That'll happen at this point up here, but I want it in terms of theta. So this is not too bad, right? Subtract a 3 from both sides, and you get 3 cosine theta is equal to 3 sine theta. Where are sine and cosine the same in the first quadrant? Theta equals pi over 4. So now I know I should fill in the other value here with pi over 4. Okay. Making progress. Formula. Area equals 1/2 integral from 0 to pi over 4 of big R squared minus little r squared. So we said the big R was 3 plus 3 cosine theta. There's your big R squared minus the little r squared, 3 plus 3 sine theta. Okay. I could expand this whole thing out, and I would if I thought there was any hope that it would simplify nicely. But look what I got. I'm going to end up with 3 terms over here, 3 terms over there, and in the end, I'll end up with a cosine squared minus sine squared, which would be great if I were working with hyperbolic functions, but I'm not. So if I saw a cosine squared plus sine squared somewhere, then I would think, all right, maybe there's a reason for me to keep going and to try to get a numerical answer. But in this case, I'm just going to leave my answer like that and call it a day. All right, so you will see sometimes, again, the return of setup but do not solve. That's why we're setting up and not solving, because these things end up being very large functions when you expand the whole thing out. All right, in the next video, we'll take a look at derivatives.